Okay, so it's time now to move to the third part. So from the first two parts, we learned some of the basics of um, how algorithms and optimizations manifestate from a systems perspective in deep learning. And from the second part, from Suparna, we heard how certain aspects on how the whole process is happening can lead into ethical problems, particularly because humans are in the loop making decisions. So now in the third part, we're going to build on top of that and also think through a new approach for doing AI that can help some of these problems. Okay, so just recapping a little bit the whole aspect about how much we can trust current processes. And so, a very interesting thought process is, given what we heard so far, especially from the second part, but also from the first part, understanding that the whole process is rather stochastic, a very interesting question for all of us is, would we trust, let's say, a bridge being built by AI or an airplane being designed and built by AI or a building in the same way that we trust those structures today being built by engineers based on mathematical models? And so that's a very interesting question. And if you think about the stochasticity of the whole thing and the chance for errors, you cannot really trust a bridge that fails, 1 out of 100 times without understanding why. So overall, this is going to create growing uncertainty and mistrust for AI. But at the same time, as we discussed in the beginning, there are really so many very real opportunities. And so our goal is to, as much as possible, utilize these opportunities while being mindful of the problems. And so one approach that Subarna brought in the discussion with the related work that she presented is that there's a whole movement in trying to involve humans in the loop, not only in terms of making decisions, but in terms of safeguarding the result, safeguarding the final result of an ML pipeline. So that can really help when we are actually utilizing AI to make sure that there's a set of people that truly understand how this AI was created and how it should be used. Of course, all of this is quite manual again, and so it doesn't really scale. And so the question is there a better way? So what does this mean, a better way? Ideally, what this would mean is that there's a process that is not so stochastic, and there are fewer opportunities to introduce bias and errors from humans. Okay, and so with that, we now move to the very last part, where we're going to try to build on top of this notion and see what we can do with that. And we're going to do again a bit of a trip in philosophy and go a few thousand years back and kind of where the beginning of science was, more or less. And so there was a time where people they were thinking that they would explain the world with kind of arbitrary ways. And then Thales was the first one to say, well, we should actually be able to reason with concrete logic about things, okay, about the human life and the physical world. And then there was a series of philosophers that kept building up around that idea for years and years, all the way to Plato, that in the end kind of characterized that whole reasoning process as an effort to start from a fundamental set of first principles that they called elements, out of which the whole physical world was constructed. And so the idea was that if we knew those 4 physical elements and we knew how they interact, something, reasoning would actually be enhanced. And so again, actually now, many hundreds of years later, in the 1600s, this is when that idea became slightly more concrete, still vague, but slightly more concrete. And so Leibniz was the first to say that, well, there are so many first principles out there in the world. If we knew all of them, if we knew how they interact, what are the rules that govern their relationships, uh, then we could know what happens every time we synthesize a solution out of these first principles. Not a solution, we synthesize a construction out of these solutions, out of these elements. And so then the idea was that, and the vision was that, well, if we then know for real these first principles and all of them, then we would actually explain everything in the physical world. And also, Leibniz had this very interesting quote, which was, "Let us calculate," which meant that if indeed such an engine existed that had the first principles and the rules, then people would never have to fight again, because whenever there was a conflict, they would just ask the engine the question, and the engine would just tell you the true answer. Okay, so in more practical terms, because this is kind of an arbitrary, kind of a bit of a vague vision, in more practical terms, this has happened in several, let's say, subfields of science. So we all know the periodic table of elements, and in principle, it is very much of the same nature. So what we have here is that we have a set of first principles. In this case, they are, the atomic number, the electron configuration, and so on and so forth. And then those are properties that if you bring together, they actually create the chemical elements. And so Dmitry Mendeleev, and actually several people before him, they were really trying to find out which are these first principles, how they connect, how these elements can be characterized, the chemical elements can be characterized. And simply, Dmitry Mendeleev was the last person to work on this vision, because his periodic table of elements was the one that kind of we all remember, but he was not the first one to work on this. There was a series of people that were trying to work in this vision, and they were all building on top of each other. And so the thing is that when this was eventually stabilized and presented, it's not that it only gave us some kind of understanding about the these chemical elements, but at the same time, it also created a structure that we could use for innovation. Why? Because that periodic table of elements was full of gaps. So there was specific sets of combinations of first principles that there was simply no known chemical element to represent them. But since it was part of the structure, scientists started wondering if those elements would actually exist in the world, and we just simply don't know about them yet. And so for 100 years after the periodic table of elements was created, scientists kept doing research to find out if certain elements in the cells that were empty existed. And this is one of the last ones that was discovered a couple of years ago in Japan. Okay, so this is what we started working on about 7 or so years ago at our lab at Harvard, wondering if it is possible to create such an engine that it would understand the first principles, understand the connections, and we could use that instead of learning. And then the idea is that if we were to do that at least for one complex problem, then we can show that it's possible, and then lots of future work can happen here. So of course we started thinking about data systems, because this is the complex thing that we are building in our field and in our expertise. So the interesting thing with complex systems today is that they're truly everywhere. And so any kind of even small innovation there, it can really have impact. And of course, the other thing today is that it's not being used only for traditional analytics, but data systems are prevalent and the core component also in the huge trend that is happening right now around AI itself. And so anything from data preparation, feature generation and storage, all the way to how models actually are being executed and scale, it is being governed by data systems. So one of the very interesting issues with data systems is that because exactly of all of this explosion in applications and in usage, and the diversity of these applications, there are continuously new requirements, both in terms of what we do with those systems, what kind of workloads they have to work with, and also the context, the actual hardware where they're supposed to be deployed. And those contexts, that context actually changes all the time. And the need for new kinds of data systems that is tailored to those contexts is growing. And of course, a very relevant aspect here of part of the problem is that at the end of the day, all of those things, they sum up to cloud costs, because if you have a system that is not optimized for the workload or for the hardware, cloud costs rise, and with big data, cloud costs really rise to the point where it becomes even prohibitive to apply systems to specific scenarios. And so, because of everything being data driven right now, data systems are the major bottleneck. And so there is a continuous tension in terms of building new data systems or utilizing existing data systems by adapting them a little bit. Of course, ideally, what we would do is we would create the perfect data system for the workload, for the hardware, for the exact application that we have at hand. But of course, we're not doing that. And the reason that we're not doing that is the complexity of building data systems. And so this is a manifestation of a very complex problem that human beings are, we don't really have so many experts in data system architecture, so we can actually go ahead and create, arbitrary numbers of data systems, every week. And so what we're doing is that we're simply adapting existing data systems to the context in the best possible way. So if we look at the process of building data systems, it's really, if we wanted to build something tailored from scratch, we would really have to have some kind of a small team of true experts with tons of years of experience, and then give them several years at a time to design this perfect tailored system. And so this is extremely expensive, both in terms of time and in terms of money, and so it simply doesn't scale. So this fits exactly that paradigm of that we're discussing in the introduction of the tutorial, of a very complex problem that we don't really have enough human experts to keep solving this problem again and again. And at the same time, even for the experts, it takes several years at a time to create these solutions. And so it's exactly a situation where if you had some kind of an automated approach, an AI approach, that would make perfect sense and would really help. Okay, so if we look internally into data systems, as you all know, what we find is fundamentally, we find data structures and data-driven algorithms. But things become truly very complicated when we think through how these data structures and these algorithms, they interact with each other. And so this is where fundamentally the complexity of data systems lies, because of everything that we want to do and the fact that most of what happens involves multiple different data structures, multiple different algorithms, and exactly what we're using and when, in what order, it really makes a huge difference in performance and resources utilization. And so what we started thinking through is, can we think about this massive problem in a way that is about first principles? So can we find a small set of fundamental design principles and rules that govern the relationships, out of which we can actually synthesize, ideally all possible systems, but because the world is such a heavy world, a massive number of data systems, way beyond what we can find out there in industry or in literature today. So what does this mean? We're gonna, since it's not possible to have a more in-depth discussion about this, it will take a lot of time. We're going to do an analogy that hopefully kind of helps people understand the primary concept here. And then people can we'll give you links so people can follow up and see more detailed materials. So what we have here is a sequence of words that they look mostly random, right? And so you can see a set of words that you understand. We all use those words, maybe even every day. And so for the most part, they look like a random set of words. So if I take here some subset of these words and we put them together in a very particular order, then we get this very interesting quote here that if you're seeing this for the first time, it feels like, oh, this is something potentially new, but even if it's not new, it's quite brilliant to think through that. And again, this happened by the interesting thing here is that this happened by us taking a subset of these goals that we all knew about, but then putting them together in a particular order creates something extremely powerful that maybe we couldn't see before. So what happened here? We started from an alphabet, okay? We started from the English alphabet here. Out of the alphabet, we created multiple different words. And then using grammar, we created sentences that are meaningful. Okay? And then of course here comes the human intuition and critical thinking to say that, oh, this is grammatically correct, but it's also interesting and powerful and so on and so forth, right? So there's this fourth level of judgment that comes from us as humans. And this is the same thing that we've done for data systems. We started by thinking, what are the first principles, the elements that characterize data systems? Out of this, we can actually create arbitrary data structures and algorithms, data-driven algorithms, as independent components. And then by being able to understand the rules, so kind of the grammar of what governs the relationships between those data structures and algorithms, what happens if we put multiple of them together to achieve a specific operation, for example, and what's the best way to do that, and so on and so forth. And that creates what we call a grammar for data systems. Now we can actually create arbitrary data systems. And given the workload and the hardware context, and given a particular data system design, then what we can do is that we can actually evaluate what would be the performance of a data system, given the workload, given the hardware, and on top of that, build search algorithms that can navigate the space. And again, we cannot go into the exact technical details here. People that are interested can take a look at the data calculator paper from Sigmod 18. There is also a tutorial in Sigmod 19 together with Tim Kraska, where we blend this kind of design approach with a learned approach. And there's also, if you look this year at Sigmod student competition, there's a paper that discusses the how we build the search algorithms using learning on top of that construction. Okay, so just to give you an idea of what are these first principles, so specifically for data structures, one of these core components of data systems, what we started doing is that we started thinking in detail through these data structures and through these data concepts that we need. And so, for example, a design principle can be how we order data in a particular node of a data structure, whether there's a pointer from this node to another node to connect them, or whether you put these two nodes together, sequential in memory or in disk, which creates certain properties. And then we also started doing clustering of these design concepts. So, for example, you see here partitioning, logarithmic design, fractional cascading, and so on and so forth. And we started clustering them with respect to whether these design principles appear in particular data structures, in particular classes of data structures. And we created this visual effectively representation of the design principles and how they manifestate in the known space of data structures. And this is what we call our version of the periodic table of data structures. And so the way you can think of this is that is like a visual summary of the actual design space that we have created in a more formal way. But what is interesting about this is that even visually now, you can see that most of the space is actually empty. So every cell here, if you see the word done, it means that we know of at least one research paper or one system that applies this class of design principles to this class of data structures. But for the most part, it is actually empty. Of course, everything about B-trees is kind of done, but for the most part, the rest of it is quite empty, which means that even after 50 years of studying data structures, there's so many opportunities to innovate and find designs that are great. Of course, it doesn't mean an empty cell doesn't mean that someone hasn't actually studied that part that combination of design principles and maybe they found a negative result for a particular context and they haven't published it, which is a side effect of the way that we publish. But really the number of combinations is so huge that this implies that there's a huge number of great designs in there. And people are still publishing about 100 new data structures per year. And so this can help us accelerate those findings. So by doing a bit of counting, we realized that we can actually create more than 10 to the 100 possible. In this case, we refer to specifically to key value storage engines. While if we look at the numbers of just pure data structures that people have published since the beginning of computer science, it's actually not more than 5,000. So the difference is so huge that it's indicative of the potential if we were able to actually navigate that space automatically or even semi-automatically and find good designs. Just for fun, here's a comparison with how many stars we estimate that we have on the sky, and so that gives you an idea of how many possible data systems exist. In our own research, one of the latest things that we're doing is that we're creating a key value storage engine using these ideas that I described here, and we find that we can actually create for mixed workloads, we can actually create key value storage engines that are 100 times faster than WireTiger and RocksDB and DynamoDB in mixed workloads, meaning that we have both reads and writes at the same time. And the cool thing here is that we can do that by designing and generating the system in a matter of seconds, as opposed to spending years with expert designers iterating through designs and so on and so forth. For more of that, you can we will link on the website some of the latest research that we have in the space. Okay, so with that, what all of this means? It means that the vision that Leibniz had as a kind of continuation of the great philosophers from the past, it might be possible. It might be possible to create this generic engine that reasons about the world. And of course, the trick is to create that for very specific problems and have concrete results. And so we have been working on the data structure space, on the key value store space, and also for the last few years, we've been investing in doing the same thing for neural network design. And we have an ICLR paper that you can take a look at in 2021, and also in image storage, which are again two very complex problems where if we wanted to have human beings figure out the design themselves, it's something that is not necessarily a scalable way to do things. Okay, and to start closing a little bit and summarizing what we discussed, there's a ton of opportunity for deep learning and ML in general to help with very complex problems in society and in science. But it is extremely crucial to have ways to truly govern how we use and how we build and how we use this technology. And this is because, again, it is the way the whole flow of development is, human beings are involved throughout this process, making critical decisions. And so human beings, we all bring with us our biases. So that has to be carefully done and protected. When we use AI, so one thing is how we build AI. When we use AI, we truly have to understand how a result, a prediction, how it has been created, and the fact that it's not really written in stone. And so any result that we get out of AI, it is a probabilistic result. And it is a result that it's truly based and created out of the data, and it is as good as the data that it was used to create that result. So it's not necessarily a prediction that comes out of AI. It's not necessarily true. It simply reflects the data that it was given. I think we all collectively as a community, we think that research in the space is only going to explode in the next several years. Exactly because of the kind of opportunity that exists here. Now, within our own space in database research, we think that there's a ton of opportunity, exactly because everything is data-driven, but specifically when it comes to how we scale processes, how we model data, thinking and creating abstractions about the complex workflow, and definitely thinking about end-to-end solutions. These are unique opportunities for the data management community, because this is exactly what the data management community brought to the analytics problem with SQL and database systems. With that, we're going to thank you for attending our tutorial. Online on our website, you can find more information about all this material. You can find links to all the related work, and you also can find this video. And we're very open to remarks, comments, and feedback. And so please stay in touch if you would like to discuss anything else with us. Thank you so much.